All right. Good afternoon, good morning, good evening. This is our last lecture video for this course. So I'm going to go ahead and share my screen as we get started, go over our course schedule. So this is our day 22 lecture. We're going to be wrapping up chapter 8, looking at sections 8.4 and 8.5. Now 8.4, as we'll see here in a moment, doesn't actually really add anything new to what we've already discussed. Rather, 8.4 kind of offers this like holistic overview of what we've done so far in chapter 8, and then just provide some different example problems working through the chapter 8 stuff step by step. Um, and so 8.4 is not really going to give us anything new to talk about. We'll talk about some of the examples there, but otherwise, it's mostly a summary of what we've already seen in chapter 8. Section 8.5, though, will be our last section, kind of new material, where our concern there is, okay, so we know how to do a hypothesis test with z-scores, which we can use so long as the sample size is large enough. But if the sample size is less than 30, then we can't use the z-scores, in which case we have to change up how we do our hypothesis test. Just as with the confidence intervals we saw in chapter 7, it is pretty much just the same methodology, the same strategy to doing a hypothesis test, only we have to use t-scores instead of z-scores. So we'll talk about that, how to use them when we have a small sample size, and that will wrap up our chapter 8 material for the class. All right. So then after this video, we will then have test 3. So that is right around the corner. I will also post some review questions you can look at, which will be available on Canvas. So if you have any questions, of course, feel free to email me, come by office hours. Happy to talk about any concerns you may have. And so test 3 will be coming up very soon. And then after that, our last week of class, there's not going to be any new assignments, no new homeworks. We're just going to have that time entirely set aside for study and review. I will post blank copies of the tests, test 1, test 2, and test 3, as well as an answer key. And you'll be able to use that to study and prepare for the final exam, as it's going to be the same kind of questions, just like the numbers are changed around some. All right. So that's coming up, and we will have the final exam on the last day of the semester. That way, it won't mix in with the regular exams you're going to have with your other classes. All right, so let's go ahead and get started in section 8.4. And as promised, they give us this nice table here at the beginning of 8.4 that's just breaking down everything we've talked about in chapter 8. Now they use this notation where they have Z subscript C. C is just it's an abbreviation for like critical, or like a critical point or a test statistic. Z subscript C is the z-score that we get from the sample data, right? It's critical to the test because that is the test statistic, which tells us what conclusion to make, all right? That uses the sample average minus whatever we're assuming the average is. So that's mu subscript 0 here. That is the assumption for what the average is from the null hypothesis, divided by the standard deviation, divided by the square root of n, all right? So we've seen this formula already. And then we have two categories. Either we're dealing with a one-tailed test, so we're only caring about one side of the bell curve, either the upper side or the lower side, or we're dealing with a two-tailed test. We can distinguish what type of test we're talking about based off of the wording in the question. Are we trying to test, is the average smaller? Are we trying to test, is the average bigger? Or are we trying to test, the average is just something different? In which case, when we say, is the average different, we don't care which side it's on, and so we have a two-tailed test in that situation. If we, so from there, we have two ways of making the decision. We can either look at a rejection region based off the confidence level, or we can look at the p-value. Both methods work. Both methods will give us the same conclusion. It's just a matter of which we prefer to use or which one will be easier, depending on what information we have or depending on the confidence level. The rejection regions are easy to do if it's a 90, 95, or 99% confidence. But if it's some other confidence level, then a p-value actually becomes easier to do. All right. So those Z alphas, they come from the table we have for the rejection regions, where based off if it's one-tailed, two-tailed, or upper-tailed, lower-tailed, that tells us what boundary we're looking for. Is my test statistic, that's ZC here, if my test statistic is far enough away and it's past the Z alpha, then we can reject the null hypothesis and accept the alternative instead. Now, if it's some weird confidence level, like a 94% or a 96%, then a p-value might be easier where we just directly calculate the probability. Well, what is the probability of my test statistic, wherever it is, of being that far away or farther? In other words, we're calculating the probability of the tail based off of the test statistic we're given from the sample data. The sample data will tell us, well, how far away the sample data is. And then based off that, we want to know what is the probability of having a statistic that far away. If that probability is small enough, if the p-value is less than alpha, then we can reject the null. All right. The only caveat with the p-value stuff that we kind of have to worry about is if it's a two-tailed test, well, then you still will find the probability of one of those tails, if it's the upper tail or lower tailed. But then since it's two-tailed, we got the upper side and lower side at the same time. Then once you have one of the tails, you have to double it to get the entire p-value. Okay? And that's all this table is. This is just summarizing the hypothesis test from everything we've done so far in Chapter 8. All right? And now this is all contingent on, first, it needs to be a random sample from the target population. And second, we need a sample size which is large enough. The sample size has to be greater than or equal to 30. So long as that's the case, then we can use the z-score to do this testing, just as we've done all throughout Chapter 8 so far. All right. So for a first example, we're returning to this rat test. And I'm going to go to the whiteboard behind me as we talk about this example. So we previously talked about this test in terms of just writing out what the hypothesis test parameters would be. All right. They're told information about what we already know about the rats in the test, where if they're unaltered, then the population of rats have an average reaction time of 1.2. So that's our null hypothesis. Before we do any testing, we are going to assume that, well, the rat's reaction time should match what the average for the population already was. For it to be different, I need sample data to prove to me that, well, this is actually wrong and it's not that, right? Now, when in this testing, they're just trying to tell, is their reaction time different? They don't say, did they get faster? They don't say, did they get slower? They just ask, is it different? In which case, we're dealing with a two-tailed test where I'm just trying to tell, is it far enough away from 1.2? All right, so it's a two-tailed test as we're looking at this exercise. And now we're also told we want to use 99% confidence. So 99% confidence. All right, in which case that means alpha is 0.01, but this is a two-tailed test. Which means, okay, as I have my alpha here in the middle at 1.2, well then for my rejection region, I'm gonna have an upper-tailed and a lower-tailed region where half the alpha is above and half of the alpha is below. All right. In which case, my z alpha over 2 here, well, this is the z where I'm looking at an alpha over 2 of, if I cut my alpha in half, that means alpha over 2 is 0.005. Okay. So what's my z alpha? What should my rejection region be? We had a table for this back in section 8.1. So we'll go back to the textbook now. I'll share my screen in just a moment. Let's see. Was it section 8.1? I think it was. Or was it 8.2? Might have been in 8.2. Yeah, it's an 8.2. So this is on page, here we go. This is on page 377 of the textbook, page 377, in section 8.2, where this tells us what the rejection regions are when I'm dealing with a 90% confidence, 95% confidence, or 99% confidence. Here we're dealing with a 99% confidence as a two-tailed test, and so my rejection region is, well, is my z value, whether it's positive or negative, I'm just trying to see, is my z value beyond 2.575? In other words, is the absolute value of z from my sample data greater than 2.575? Okay. So I'll turn off the screen share so we can update the rejection region here. We're checking if the absolute value of z is greater than 2.575. That's when we will know to reject the null hypothesis, right? So we go back to the exercise in 8.4. And, well, first they give us this table with, they sampled all 100 rats who had been injected. So here's our sample data. We have a sample size of 100. And from that sample, we can calculate an average. We can calculate a standard deviation. And I'm not going to have us do that here because, well, there's 100 rats in the sample here. So that'd take a while to put that on the calculator. But they have calculated it for us where the sample average is found to be 1.0517. And the standard deviation is found to be 0.4982. All right, so we have all of our sample data. All that's left is to actually perform our z-test and see, well, what is the z-score that goes with this sample data? If it lands in my rejection region, then great, we can reject the null hypothesis. If it doesn't, then we'll keep the null hypothesis, okay? So at first, it looks like maybe the rats have gotten faster, but, who knows? Is it just a fluke that these 100 rats just so happen to have an average that was a little bit lower? How will we know if it's a fluke or not? Well, we can look at the z-score to see how far away is it. Is it far enough to land in these rejection regions? Okay? So we calculate z, the test statistic. Now here in section 8.4, they're using this notation z subscript c. This is just the test statistic from the sample data. So I'm going to have 1.0517 minus 1.2 divided by 0.4982, 82, divided by the square root of 100, which, easy enough, that's 10. All that's left now is to put this into a calculator and see what we get. All right. I left my calculator in the other room. I will be right back. All right, I have returned, and so now we go to the calculator. We're looking at our z-score. We have 1.0517 minus 1.2 divided by, and make sure this denominator is also wrapped in parentheses, 0.4982 divided by 10. And as I put all of this into a calculator, I'm getting a z-score of negative 2.977. All right. the absolute value of that is positive 2.977, which is beyond 2.575. So even with a 99% confidence, this z-score is way over here to the left. It is super unlikely that I would have sample data which is this far away. In fact, with 99% confidence, I shouldn't have sample data that far away. So because I do, this then gives us 99% confidence that we should reject the null hypothesis. Reject the null hypothesis and accept the alternative. All right. Now, the thing about this test is that we did not prove that the rats have gotten faster, right? Look back at the alternative. The alternative was that the average is different from 1.2. So we haven't proven that they've gotten faster. After all, it could be, what if I repeat the test and they get an average which is actually slower than 1.2? If it's like 1.4 or 1.5 or something, right? So this does not prove they've gotten faster. All we've done here is proven that, well, it doesn't seem to be 1.2 anymore. We would need to do more testing to determine have they gotten faster or not, or we would need to change how we ask the question and change what is our alternative here, right? In which case that would also change the rejection regions and possibly change results here. So all we've done here is just shown that we don't think the average is 1.2. We think it's something different. All right, and so that was this question fully worked out from start to finish. Let me nudge this down a little bit so you can see, yeah, H alternative down here. Okay. So 8.4 then continues to go through several other examples. It's rinse and repeat the same thing we've done here on the board, okay? Just different types of tests, upper-tailed, lower-tailed, two-tailed, so on and so forth. But it's always the same kind of methodology. What I want to turn our attention to is in section 8.5, where we talk about, okay, so long as the sample size is large enough, then we're good. We can use all the z-score stuff, okay? But what if it's not large enough? What if my sample size is too small? And for this, we're actually going to turn to, there's this very first example in 8.5, and this is also our participation question for today, all right? So we can go ahead and pull up the participation question as we're examining this. Let me share my screen here. Sharing my screen, okay. So a pH below 7 is acidic, if we're talking about chemistry, all right? A pH which is above 7 is alkaline, and a pH of 7 is considered neutral. Now, for some water treatment plant, they have a target pH of 8.5. They want it to be slightly alkaline, or in other words, they want it to be slightly on the basic side. That's generally like considered healthy or better for you. But they just want to make sure that it's not acidic, right? Nobody wants to drink water that's acidic. Now, in order to make sure that the water treatment plant is working as it's supposed to, they do hourly testing to see, well, what is the pH of the water that we're treating here, right? And so the mean and standard deviation of 1 hour's test results based on 17 water samples at this plant, and we have some sample data here, all right? Now, some reasons why do we only have 17 water samples? I mean, if this is maybe a smaller town or a smaller water treatment plant, they just might not have the ability to take as many samples, or there's just not as many different pipes to test. So for whatever the reason, they only have these 17 samples. So this is not large enough to use the z-scores that we just did. We still have the sample data, and we're trying to determine, is there evidence that the pH level in the water is different from 8.5? Now again, notice the key words here. It doesn't say, is the pH below 8.5? It doesn't say, is the pH above 8.5? Just says, does it differ? Because of that, this is another two-tailed test like we did on the board, okay? So I'm now going to turn to the board behind us. Also, you can see here, This doesn't specify what kind of confidence we're talking about, right? It doesn't say 90%, 95, 99. So if you're dealing with a question where it doesn't specify the confidence, you can just assume that we're talking about 95% confidence, okay? Now on the test, I will be more clear on that. I will always state what confidence level we're using. But for the sake of this exercise, if it doesn't specify, then assume we're talking about 95% confidence. Okay? So I'm going to turn off the screen share here as we're talking about this next example. All right. And we're dealing with a two-tailed test as we're only trying to check if the sample data proves that the pH is different from 8.5. Because if it is different, well, then maybe the water treatment plant needs to adjust how they're treating the water, or maybe they need to double check, is the treatment plant working correctly? Or is there something else going on where the water coming into the plant for some reason is more contaminated than usual? In which case, they want to track down what's going on with the water if the pH is different. Okay. So at first, we assume the water is working as normal. The average is supposed to be 8.5, and we're trying to show or see, does the sample data suggest that the average is something different? All right. We're working with 95% confidence, which means alpha is 0.05, and we're dealing with a two-tailed test. Oops, let me make sure it's all on the screen. Okay, yeah, that's on the screen. We're dealing with a two-tailed test. So I have my assumed average here in the middle. And then I can have these rejection regions to the left and right. Half of the alpha is below. Half of the alpha is above. And I need to figure out the rejection region with this 5% or this 5% error, right? Or 95% confidence. But that means this region here on the right side has 0.025. All right. That also means this on this side is 0.025. Now I can't use z-scores because the sample size is too small. So I have to use a t-alpha instead. So I need a t-alpha instead. Now we already know the sample size for this exercise is 17. Now recall when we talked about t-scores back in chapter 7 with confidence intervals, in order to calculate some t-score, we needed to know the degrees of freedom. Degrees of freedom are always the sample size minus 1, or in other words, 16. Okay, so we have that much information. So how do I know what t-score to use? Well, luckily, the textbook provides a handy-dandy table just for this question, so we don't have to do any kind of calculus to figure out what is the t-alpha to use for this exercise. So as we go into the textbook, in the appendix, let me share my screen here so you can see where I'm going. Down in the appendix, Appendix B, we have these tables called critical values of t, Table 3, right? This is the table we want to use. Now, the way to read this table, previous tables have given t-scores or z-scores to tell us a percentage between the middle up to some t value or z value. But look at this table where the shaded region is. This is telling us the area of one of the tails. Now, in this picture is only showing one tail, right? So we have to be careful. Alpha for this question is supposed to be 5%, but my upper tail is not all of alpha by itself. My upper tail is actually alpha over 2. So in this picture, as I'm trying to find t for this upper tail, I have to think about t when I have subscript my alpha over 2. All right, so I'm not looking at t alpha. I'm looking at t alpha over 2. So on the board, alpha over 2 is 0.025, and I need to find the t-value which corresponds with that tail, right? I want to find a t-value where this right tail, it says alpha, but forget about that for a moment. We're looking for what would be our alpha over 2. I need this blue region on the right side to be 0.025, right? Half of alpha. So to read this table, I look in the column with the alpha I'm looking for. So for this question, I'm looking for the t where it's subscript 0.025. So I'm looking in this third column. And then with the degrees of freedom for 16, so I'm looking in the 16 row. And then in the column here for 0.025. And so degrees of freedom 16. My subscript is 0.025. Our t is 2.12. 2.12, all right? This is then our rejection region. This is the boundary, just like the z alpha when we were doing the z-test, all right? This is telling me how far away does my t need to be in order to reject the null hypothesis. Now, this is a two-tailed test, so my rejection region is just checking to see, well, regardless of whether it's positive or negative, is the absolute value of z bigger than 2.12? If it is, oh, not z, we're looking at t now. If it is far enough away, then we will reject the null hypothesis, okay? All that's left now is to calculate t from the sample data. So now we can go back to the exercise. The sample size is 17. My sample average is 8.42. And my standard deviation is 0.16. All right. Which you can also see here with this natural variation. With a standard deviation of 0.16, well, then sometimes this average might waver a little bit and actually be above 8.5, in which case 8.42 might not be alarming at all. How do we know if it is alarming? Well, we're just trying to check if this t-score is far enough away from the middle. All right, so we calculate t using the same formula as before. So t is equal to 8.42 minus 8.5 divided by our standard deviation divided by the square root of the sample size. Put all of this into a calculator. And we get for this exercise 8.42 minus 8.5 divided by 0.16 divided by the square root of 17. And we have a z-score, or a t-score, not a z. We have a t-score of negative 2.062. Which, okay, maybe that's a little bit big. So it's a little bit far away from the average. But with a 95% confidence, it's not far enough away. I would need to be beyond 2.12 to reject the null hypothesis. So because it's not quite far enough away, we're actually going to keep the null hypothesis. 8.42 is a little bit low, and so maybe we would want to just continue taking measurements and make sure it doesn't like keep dropping or something. So long as, it's not changing more, then this isn't too alarming based off the information we're given. The water's not acidic. It's maybe dropped a little bit in pH, but not an alarming amount. All right. And so we have our final answer here for this exercise. So I'm just double checking something here. Yeah. So this is not far enough away to reject the null, in which case we keep the null hypothesis. Okay. Oh, my K does not look good there. Let me fix that. K. Keep the null hypothesis. So as we go back to the question, then what is our final answer? I'll share my screen here again. Does the samples provide sufficient evidence that the pH level differs from 8.5 The answer is no. If we keep the null hypothesis, that means the average is 8.5 still. It just so happens that the sample kind of wavered a little bit, could just be bad luck, dumb luck. But it is not far enough away to suggest that the population average has actually changed. All right. So the answer is no. Well, in fact, you can just leave it at that if you want. Just typing in no, there's not evidence to suggest the pH level differs. Um, yeah, we keep the null hypothesis here, all right? Um, there is not sufficient evidence, okay? And we can leave it at that. Now, if this were a test question, you would, of course, need to show all your work. You would need to show, that we are keeping the null hypothesis, and therefore that is why there is not evidence to suggest that the pH actually differs from 8.5. Okay? And so that will wrap up our Chapter 8 material. The rest of 8.5 just continues looking at other examples of this kind of stuff. But otherwise, there's no other curveballs. This is the entirety of the material for Math 208. All right. So I'll go ahead and stop here. It's been a pleasure teaching the class and talking with some of you. If you do have any questions, of course, please feel free to email me. I'm happy to talk about any concerns you may have with the class. Otherwise, I wish you all the best of luck. And, well, maybe I'll see you in my office or maybe I'll see you in another class. All right. Have a great day. And I will see you another time, maybe. All right. Bye for now.